I'm very happy to introduce Dr. Swapna Panickal, my colleague and senior scientist at the Center for Climate Change Research in IITM. Swapna is basically leading our Earth System Modeling group at the CCCR in IITM, and she holds a PhD degree in Marine Sciences from Goa University, and a MTech in Atmospheric Science and a MSc in Oceanography from Cochin University of Science and Technology. So with her strong background both in atmospheric science and oceanography and her expertise in ocean modeling, so Swapna played a key role in the development of the IITM Earth System Model. In fact, the coupling of the atmospheric component, the GFS, and the ocean component MOM4, she was instrumental in that, and this was the first success in getting our ESM, and she has also worked. Her interests include ocean dynamics, air-sea coupled interaction, sea level variability and change, and recently she has also started working on extreme sea level variations and interactions with tropical cyclones, storm surges, and so on. And Dr. Swapna is a lead author of the IPCC 6th Assessment Report in the chapter on future climate projections. She is a member of the working group on coupled modeling of the World Climate Research Program. And more recently, she also was elected as a member of the working group of the WCRP Lighthouse project on safe landing sea level rise. And her work has been recognized, and in honor of her contributions, she was awarded the Certificate of Merit by the Ministry of Earth Sciences in 2016, and also the IITM Silver Jubilee Award 2016. With this brief introduction, I welcome Dr. Swapna to give the talk. Thank you.
Yeah, good afternoon, everybody, and thank you, sir, for the nice introduction. And my thanks to the organizers for giving me an opportunity to provide a talk here. So, myself, Swapna Panickal, I am from Center for Climate Change Research at IITM. I work on the climate modeling and also on the sea level research. So in this talk, I'll be focusing on our efforts towards the developing the IITM Earth System Model, and also some aspects on the sea level research, what is being carried out at the Center for Climate Change Research at IITM. So the left panel, it is a schematic of IITM Earth System Model. So this is the model that has contributed for the CIMIC, that is the Coupled Model Intercomparison Project of WCRP, and also it is also contributed for the recent IPCC 6th Assessment Report. So basically, the IITM ESM, the atmospheric component is the global forecast system, and the ocean model is the MOM4 P1, that's the modular ocean model, it is GFDL. So this ocean model is also having an interactive biogeochemistry module that is called the TOPAZ, which consists of more than 41 traces of the biological components. And it is also having an interactive sea ice model, which is called the SIS, and there is a land model that is NOAA LSM. So this is the basic structure of IITM ESM. And the right panel is showing the ESTF server, which is located at CCCR IITM. So whatever simulations we have carried out, all the data sets from the model simulations are disseminated publicly through the ESTF server, which is located at CCCR. And this server is also used for disseminating the data from the CODEX experiments. That is also an WCRP activity, the Regional Climate Model Downscaling Experiment, in which the AGCM atmospheric model is forced with the boundary forcing from the CIMIC, and this is more used for more regionally focused studies. So both of these data sets are available for research for the publicly, and we are all publishing our data through the server at CCCR. So today I will discuss briefly about our efforts towards the IITM Earth System Model development. Dr. Krishnan must have yesterday already talked in detail about this. So I'll be just giving few slides on this, and I'll be moving on the sea level research because greenhouse gas concentrations has been increasing and it is impacting the climate system. And one of the catastrophic consequences of the rise of the climate change is the rise in the sea level. So we'll see little more details about how the sea level is rising, what are the processes that are contributing to the rise in the sea level, and how can we use the climate model for understanding the sea level rise and see like how they are projecting the rise in the sea level for the future. And some aspects on our next generation IIT-MES. So as I told, like we have started, like CCCR was established in 2010, and with the objective of developing a climate model, so we started developing the IIT ESM Earth System model, and we started with the climate forecast system of NSUP CFS. And first, what we did was that because CFS has already shown good skills for the seasonal monsoon prediction of the South Asian region, and it has been already employed at IITM for both the seasonal and extended range prediction. So we use the climate modeling framework, the CFS, as the base to start our IITM Earth System model development. So first what we did was that first we did a climate 100-year control simulations with the CFS, and first we evaluated the model. So what we have seen is that there is a huge energy imbalance because there was a major climate drift because it's a seasonal prediction model. And when it was employed for the climate simulations, it was having a huge energy imbalance, roughly 6 watts per meter square. And our idea is to address like when there is an increase in the greenhouse gas concentrations, there will be increase in the radiative forcing. And we would be like to address like what is this impact on the climate system. So with a 6 watts per meter square energy balance in the model, we won't be able to address all these aspects. So we started our development from that point. So first we focused on improving the ocean model because ocean is having a huge memory. It is having a large heat capacity, and most of the energy imbalance in the climate system is absorbed by the oceans. So we started first with the ocean component of the model. So we have introduced the MOFO P1, that is from GFDL. We have coupled the MOFO P1 to the IIT VSM. And it is also having an additional benefit, like it is also having an interactive biogeochemistry component. So we will be, in addition to the physical aspects, we will be also able to study the biological interactions with the physics also with using this model. So this was the first paper we have published in BAMS in 2015, wherein we included the MOFO P1 in the model, and we did 100-year simulations. And first we evaluated the mean state, whether there is some improvement in the mean state compared to the previous version. So the left panel is the sea surface temperature bias, which was shown from the IIT VSM and also from the CFS version 2. And we can see like in the CFS V2 was having a cold bias. That means the tropical SSTs were colder than observed, as we can see from all the blue shades. And there was a large deep MLD biases also was reported with the CFS. Once we improve the ocean model, because this MOFO P1 is having a better physics as compared to the previous version. And also like submesoscale parameterizations are also being included in the MOFO P1. Because of all these changes, there was an improvement in the mean state that is also reported by our standalone studies. We have also done the standalone MOFO P1 before coupling it. So that has also shown that MOFO P1 is better in state representing the ocean mean state compared to the MOFO P0. So when we coupled the MOFO P1, we were able to reduce the biases of the tropical region, especially in the Indian Ocean. We can see that the cold SST biases has been improved, but still there needs to be improvement in the mean state, as we can see that the subtropical gyres both in the Pacific and Atlantic still is having a cold bias. So we'll be addressing these aspects in our next version. But still we can see that the Atlantic bias, cold bias has been improved, and Pacific bias also is improved in the IIT ESM. Then also we looked at the modes of variability, like how the ENSO, because ENSO is the dominant mode of variability that is affecting the monsoons. So we looked like how these modes are interacting and how they are affecting the monsoon in the model. So this is just an example, like tride panel shows like this is the EOF of the tropical temperature, Pacific temperatures. First EOF represents the ENSO variability. And we can see that like we compared with observations. So the basic structure of the variability in the Pacific is similar to the observations, and the variance explained is or more or less similar to the observations. So this is one of the aspects. We also looked at the other modes of variability, like on the multi-decadal scale, PDO, Pacific Decadal Oscillation. That is another mode of variability that is having a major impact on the monsoons. So how these modes interact with the monsoon, that was the mean state improvements and the interaction of the modes of variability with the monsoon. That was addressed in the first stage. Still we were having the problem of energy imbalance of 6 watts per meter square. Since we have improved the ocean model, then we focused on achieving a radiatively balanced framework. So for that, we have to improve the coupling between the ocean and the atmosphere, because atmosphere provides the heat and momentum fluxes, and these are used by the ocean model, and ocean model provides the SST and the ice concentrations to the atmosphere. So these are done through the coupling processes. So if there are problems with the coupling processes, these are not properly represented in the climate model, we could have this type of energy imbalance. So then we focused on achieving the radiatively balanced framework. So first of all, we have seen that in our first version of the model, there was a larger depletion of the sea ice. Arctic ice was getting depleted. And so that is producing a lot of ice albedo feedbacks and the warming and melting of the ice over these regions. So first we have to remove the ice model from the AGCM, and we use the CI simulator from the ocean model for representing the sea ice processes. And we also implemented the partial grid implementation. That means that the model what we are using, because we have to perform long simulations for the CIMIC. So we have to use a relatively coarser setup, coarser version of the model. For that purpose, we used a T62 version, that is roughly 2 kilometer version for the atmospheric component. And ocean is a tripolar grid that is varying, like near the equatorial regions, it is roughly 0.5 degrees. And if we move forward, it is becoming coarser, like it is roughly 1 degrees. So when there is an exchange of fluxes that is happening between the atmosphere to the oceans, that there is, we have to consider like there is a bigger, wide or coarser atmospheric grid, and there is a finer ocean grid lying underneath. So these fluxes has to be exchanged properly, then only it will identify land, ocean, and ice processes properly. So we have also implemented a partial grid implementation so that it will understand like whether it is a land point, ocean, or ice, so that the fluxes are being properly passed between the different components of the models. So that was a breakthrough, like when we could improve those processes, we from the 6 watts per meter square energy imbalance, we could achieve an imbalance. Our energy imbalance was reduced to 0.5 to 0.8 watts per meter square. So that was the first stage of development. And then again, we have to test our model simulations. So again, we have performed the control simulations. So this is the spin up we have done a 300-year spin up, and we slowly introduced only the aerosol tropospheric volcanic forcings, like 1850 condition. What was the GHG values for the 1850? We slowly introduced that, and we again did another 700-year simulations. So top panel shows the pre-industrial temperature, which is roughly 13.8 to 13.9 degrees. This is the global mean averaged annual mean temperatures, which is comparable with the observations. And the bottom panel is the energy imbalance, top of the atmosphere energy imbalance, which is also less than 1 watts per meter, so roughly 0.8 watts per meter square. And it is not increasing, it was steady. That means that the model is attained at a steady state, wherein we can consider incorporating other forcings. So this was the next paper, which was published in James, wherein we started applying. First, we did the control simulations, and we identified like how is the energy imbalance improved in the model, and what are implications for the global climate drivers, like how is the AMOC, Atlantic Meridional Overturning Circulation, has been represented in the model, and how is the Arctic ice loss is improved in the model. So these aspects, we first, because they are the major climate drivers that has having global teleconnections. So these aspects have been addressed first. And then we started introducing the different forcings. This is just an example, like land cover changes, because we are doing the CIMIP simulations. So we have taken the forcings under the CIMIP 6 protocol, And this has to be incorporated in the model, and we have to test it, and we'll do the simulations. So this was the 18 with land cover during the pre-industrial period, 1850. And this is just a representation like for the present day, 2007. And we can see like over the Indian region, all the green colors, they represent the crops. And so we can see like the green color represent the forest and the red color represent the crops. So we can see like the pre-industrial period, there were a lot of forests, and from this to the present day, they are becoming the croplands. So there's a large tropical deforestation that is happening. So a model also has to represent this, because this has an impact on the biophysical feedbacks, like it can impact the albedo changes, evapotranspiration, and also the biochemical like carbon emissions. So these all will have the couple of processes has to be represented. So this is one of the example like how we have included the land cover changes in IITM ESM before starting our simulation. Then we followed the SIMI protocol, and we have done a pre-industrial control simulations wherein we fixed all the forcings like GHG, aerosol, all these concentrations we have kept for the 1850 values. And we have done a 800-year spin-up by control simulation with the model. Once the model has reached a stable, steady state, we started the other simulation. There is a transient CO2, wherein we increase the carbon dioxide concentrations 1% per year, so that we will be able to understand the transient climate response. That means that how much the amount of global temperature increase per increase in the carbon dioxide concentrations. Similarly, the quadrupling carbon dioxide. These are all try to understand the climate response. Then we actually did the historical simulations, wherein we forced the model with all the historical forcing, yearly varying historical forcing for the 1850 to the 2014 period. That is the historical simulations. We also did an IMI, that is only atmospheric model with prescribed SST. And we have also performed the future projections. So for the future projections, we have followed the IPCC scenarios. So according to the IPCC and the SIM protocol, they have developed a new set of scenarios. It is called the shared socioeconomic pathways. That means that it's a combination of the socioeconomic conditions and also the radiative forcing. So they range from SSP1 to the SSP5. And if these also include the scenarios which contains very high and high carbon GHG emission. That means that the carbon dioxide concentrations roughly double by 2050 and 2100 respectively for the high and very high scenarios. And in intermediate scenario wherein the CO2 concentrations or CO2 emissions are fixed at the present day values till 2050. And also there are scenarios where low and very low scenarios. They are called the SSP 119 and SSP 126. That means that where the CO2 concentrations are reduced and they attain a net zero by 2050, followed by the GHG emissions. So once we did all these simulations, we will be able to understand the future climate response under different pathways, like how we also need to consider the economic conditions, economic growth, and also need to see how the radiative forcing will have an impact on the climate system. So based on these scenarios, the future projections are being made. So this was the first thing, after this, our models simulations were carried out. We also looked at the observed changes in the climate system, and there was a report book, Assessment of Climate Change over the Indian region, that was brought about by the Ministry of Earth Sciences, Government of India, and wherein we look more focusedly on the regional change over our region, our Indian region. And these are the projections from the IITM ESM, along with other SIMIP6 models. And all the solid lines shows the projections from our IITM ESM, and other models are shown with the dashes. So we can see like black curve is the observed increase in the temperatures, and the project from IITM ESM, the global mean temperature is projected to increase by 4 degrees. This is with respect to the 1850 condition, 1850 to 1900 conditions. So that we can expect a 4-degree warming by the end of the century. But we have to also see that the SIMIP6 models, the range is very high. They range from 3 to 6.5 degrees centigrade. It has also been reported like SIMIP6 models are producing a higher warming as compared to the previous SIMIP5. So I will briefly discuss these aspects in the later slides. And the precipitation is projected to increase. And even the recently published IPCC report also shows that there will be, because temperature is increasing, the moisture holding capacity is increasing, and there will be an increase in the precipitation. And over the South Asian region, the annual and the summer monsoon precipitation is projected to increase by the end of the century. And along with the increase in the temperatures, the sea level is projected to increase because we know more heat is taken by the oceans. So there will be thermal expansion. And also because of the melting of the glaciers like Antarctic and Arctic, these glaciers are melting and they also add more mass to the ocean. So there will be an increase in the sea level. So this is just a thermospheric component. Just because the temperature is increasing, how much is the sea level projected to rise? This is from the IITM ESM. And this is a spatial map which shows the change in the projected change in the thermospheric sea level by the end of the century. So we can see that the sea level is projected to increase in our region, Arabian Sea, Bay of Bengal, Eastern Equatorial Indian Ocean, South Indian Ocean, it is projected to increase. So as I told, like the model.
Sorry, when you say sea level increasing in these different scenarios,
yes.
Do you have some kind of precise prescriptions for cities like Mumbai, Chennai, Kochi?
Yes, I have. I'll come to that in the coming slides.
Thank you.
Yeah. So this is just like before going to the sea level, I thought like how the climate models are projecting the temperature. That is very important to understand, like what is the projected temperature. Then what is the projected increase in the global mean sea level, that and our regional aspects I can discuss a little bit more. So this has been shown that 6 models are having a high climate sensitivity, like it is ranging from 1.8 to 5.6. Climate sensitivity means it is the hypothetical warming with the doubling of the carbon dioxide concentrations. And 5 models, it was assessed like it is will be between 1.5 to 4.5. So there is an increase in the global temperatures in the 6 models. IIT ESM is having a relatively low climate sensitivity, roughly about 2.8 degrees Celsius. So we are having our projected temperatures are roughly 4 degrees by the end of the century as compared to with respect to the pre-industrial period. So to assess the projected changes in the temperature, IPCC report also used the constraint projections because we know what is the warming that has been occurred in the recent decades based on the observations. So we can use this information to assess what is the projected change in the temperature in the future. For this, energy balance models are used. So we estimate the equilibrium climate sensitivity, and these values are fed into the energy balance models. And we use, like it is called an emergent constraint. Like we have the observed warming period. We can use this to address how much will be the warming for the future. So left panel is the unconstrained or the rose MIP outputs, which is showing how much is the warming from the different scenarios, which is ranging from SSP 119, that is the very low end scenario, to SSP 585, that is the very high end scenario. So this is the projected warming from the rose MIP 6 models. And right panel is from the constraint projections. We can see that the constraint projections are lower on the lower side as compared to the unconstrained. Still, we can expect like global temperatures are projected to increase more than 4 degrees by the end of the century in a very high end scenario. And when we compare AR6 with AR5, again, we have, because recently we have got more data, we have got more satellite information coming in. Globe is widely covered with the satellite observations, and the observed warming is higher than the previous. Every decade is warming much more than the previous decades. So the observed warming itself is higher. So that whatever be the projected models, we can expect that there will be much more warming in the future or in the coming decades. So this is just an example like how the temperature is projected to increase in the future. So it is ranging from the very low to the very high scenario. So whatever may be the scenario, we can see like whatever may be the pathways of the greenhouse gas emissions, global mean temperature is projected to increase. And the IPCC 6 assessment report clearly shows that we will be crossing 1.5 degree warming in the next 20 years. Like between 2020 to 2040, we'll be crossing 1.5 degrees centigrade. And a very high scenario can go up to more than 4 degrees. And if we follow the present day emissions, that means that if we keep the CO2 levels for the present day, that is shown by the SSP 245 intermediate scenario, still we will be crossing 2 degree warming by the end of the century. So we know like if there is a perfect balance between the incoming radiation and the outgoing radiation, there won't be much warming in the climate system. But because there is an imbalance, there is more greenhouse gases are being emitted, so they trap more of the radiation. So there is an imbalance is happening. And where is this most of the heat going? Because this has to be getting accumulated somewhere. It is taken by the oceans. So we see like more than 90% of the heat imbalance is taken by the oceans, which is much higher compared to the other components, like atmosphere is contributing only to the 4% increase, continents 5%, and ice 7%. So ocean act as a heat source. It acts as a sink for the most of the heat imbalance in the climate system. So obviously it will have the consequences, like there will be rise in the sea level. So if you see from the IPCC report, the CO2 concentration, they are the highest in the human history. So the temperatures are warmest and they are increasing everywhere, and the sea level is projected to increase. Report shows that sea level will be the fastest rise in the last 3,000 years. And there's a melting of the ice, both the Arctic sea ice is melting, glaciers are also retreating. So all of them will add more mass to the oceans. So there will be much more rise in the sea level. So this is the observed increase in the sea level. Again, for the global oceans, starting from 1870, this is based on the paleo observations and also based on the tide gauge data and recently from the satellite data. So we can see like from the based from the paleo reconstructions and the tide gauge observations, there was recorded like roughly 1.7 millimeter per year is sea level is rising over the globe. But we have the satellite data from 1993 onwards. The satellite altimetry has come. So we are able to monitor the sea level globally. And we are able to get the sea surface height information globally. So the recent data from the satellites shows that since 1993, sea level rise has been accelerating at a rise rate of 3.3 millimeter per year in the global oceans. So sea level is projected to increase. So the IPCC report also shows that by the end of the century, sea level can go up to 1 meters in a very high-end scenarios. And by 2300, it can go up to 3 meters in a low-end scenario to 7 meters in a very high-end scenario. Still, we need to consider like in the near future, like another 20-30 years, there is a roughly 10 centimeter to 15 centimeter or 20 centimeter sea level rise is projected for the global oceans. So let us see what are its implications for our region, our Indian Ocean region. We have to consider like sea level rise is highly non-uniform. There are different processes that they are contributing to the rise in the sea level. Like we can consider because the ocean atmospheric dynamics has a larger impact, changes in the circulation, winds, all of this contribute to the changes in the sea level regionally. So broadly, we can say like there's changes in the volume, like when there is an increase in the temperature, there will be thermal expansion that can increase the sea level. That is called the thermospheric sea level. And when there's salinity changes, that also changes the density. And that is called the halospheric. So these two terms, thermospheric and halospheric, contribute to the spheric changes. Along with this, the subsidence, because many of the land vertical subsidence are happening, that also can contribute to the rise. So just an example, like the Bay of Bengal region, Diamond Harbor, where sea level rise is roughly 5.5, more than 5 millimeter per year. That is mainly coming from the vertical land subsidence. So this is the spatial map of the sea level trend from the satellite data from 1993 to 2020. We can clearly see that the sea level is rising in the Indian Ocean, Arabian Sea, Bay of Bengal, and it is higher to the other regions like Western Pacific is increasing, Equatorial Atlantic is increasing, but we have a higher sea level rise in the Indian Ocean. And our coastal regions are densely populated, like many. So this rise in the sea level will have implications for the coastal population. If we estimate the sea level trend in the Indian Ocean, it is 3.5 millimeter per year, and the global is 2.93. So that means that Indian Ocean sea level is accelerating in the recent decades. And we have got many tide gauges along the west coast of India and east coast of India. For example, Mumbai, we have the tide gauge observations starting from 1880s, more than 100 years of observations we have from Mumbai tide gauge. And all of this data, whichever tide gauges we are observing, like all of them are showing like there is an increase in the sea level in the Indian Ocean, and there are different regional variabilities, like just south of the equator, there is a drop or fall in the sea level. So different oceanic processes are contributing to the changes in the sea level along with anthropogenic contribution. So this was a study wherein we try to understand what is the cost, one of the costs for the increasing sea level in the North Indian Ocean. So on a climate change perspective, we can say like the monsoon circulation has been weakening for the last 50 to 60 years. And once the monsoon circulation is weakening, there is a southwesterly monsoon winds. And if you see the meridional heat transport in the Indian Ocean, it is directed southwards because as per the Ekman dynamics, the flow is to the right of the wind direction. So it is directed southwards from May to October month during the monsoon and transition months. And other season, it is directed to the northwards. But we have strong forcing coming from the monsoon winds, southwesterly monsoon winds. So the meridional heat transport in the Indian Ocean is dominated by the summer monsoon winds, and the heat transport is directed southward. So when there is a weakening of the monsoon winds, that means that the heat transport is also getting weakened. More heat is getting retained in the North Indian Ocean, and that is producing the sea level rise in the North Indian. That is one of the cause for the rise in the sea level in the North Indian Ocean. And this is again from the satellite data. And we can see like the different coastal locations. And what we have done is that we have the tide gauge information from these coastal stations, but tide gauges have a lot of data gaps. So we won't be able to assess the continuous change of sea level along our coastline. So what we have considered is that we located the tide gauge stations and wherein that we correlate with the satellite data, and we looked at like were around 100-kilometer radius of the tide gauges. What is the observed sea level from the satellite, and how is it comparable with whatever available data from the tide gauges? And this is the observed sea level. Based on this trend map is prepared. So this is the sea level trend along our coastline based on the satellite information. So we can see like all our coastline, as you were talking about Mumbai also has more than 3 millimeter per year increase in the sea level in the recent years. So this is from based on the sea level satellite observations. Similarly, all the stations in the Arabian Sea coastlines also increases. In the Bay of Bengal also, in the head bay, there is a wind high more than 5 millimeter per year. That is because of the land subsidence. Similarly, Chennai, Vizag, everywhere there is a rise in the sea level. There is more than 3 millimeter per year is recorded from the satellite observations. So how can we use this for the societal application? This is just an example I am giving. Like there is we have provided the mean sea level projections for the Kalpasa Dam project. This is a proposed dam over the Saurashtra region where, because there's a lot of water scarcity and there's a reduction in the groundwater table, and also there is a water scarcity. So the Gujarat government is proposing to build a dam across the Gulf of Kambat. It is a 30-kilometer long dam they are proposing. So to construct a dam, we need to consider all the coastal processes, the bathymetry, and also what is the projected mean sea level rise across that region. For this, we looked at all the 6 projections, and we try to see, like we again correlate with the observation. We have the tide gauge observations with certain stations like Bhavnagar, Mumbai, and Oka, and all those regions. So we try to correlate these model observations with the observed tide gauge data, and then we looked at the projections. So we see that Bhavnagar is the location where this dam is proposed. So there is Mumbai, there is a 0.17 by 2050. We can expect a 0.17 meter increase in the sea level by 2050, and it is up to 0.46, roughly 0.5 meters by 2100. Similarly, different locations we can see like from 2050 to 2100. This is based on a medium scenario. We have not considered very high-end scenario. Based on a medium scenario itself, we can expect this much of sea level rise along our coastal regions. So because we need to consider that there is an increase in the sea surface temperature globally. And if you see for the Indian Ocean, even the recent IPCC report also shows that the sea level in the Indian Ocean is warming at a higher rate. This is because of the geographical specialities, because Indian Ocean is landlocked to the north. So heat is not transported to the northern polar regions. And we have a very shallow overturning circulation. So whatever heat that is taken is accumulated from the climate system that is being stored in the upper few hundred meters in the Indian Ocean. As a result, the sea surface temperatures are rising at a higher rate in the Indian Ocean. This is highlighted in the IPCC report. And we see that because there is an increase in sea surface temperature, sea level is definitely going to projected to increase. Along with the rise in the sea level, the intense cyclonic systems are also increasing. This is a recent study wherein we looked at how the intense cyclonic systems are increasing in the Indian Ocean. So we generally know like the tropical cyclones have a bimodal structure. They form during the pre-monsoon and during the post-monsoon season. But generally the cyclonic number is more during the post-monsoon season. But when we look at the intense systems, we can see like in the recent years, the intense systems are forming more during the pre-monsoon, especially during May month. More intense systems are forming in the Indian Ocean. This is considering both Arabian Sea and Bay of Bengal. So we try to understand why this is forming more. It is again associated with the increased warming of the Indian Ocean. The potential intensity is increasing and the monsoon is also weakening. So there's the weakening of the wind shear. So there's a dynamic contribution and also the thermodynamic contribution. Both of them are favoring so that we are having more intense tropical cyclones in the Indian Ocean in the recent years. So what are its consequences for the sea level? So when the temperature is increasing, there will be an increase in the volume, there will be an increase in thermospheric sea level. Along with that, when the cyclones are forming, they produces more of the surges. So when all of them, and we already have like our tide, if you see the tidal distribution, we have very tidal values going very high from the southern tip of India to the northern part, both west and east coast of India. So there is an increase in the tidal range, and also there's an increase in the mean sea level. And the intense cyclonic systems are increasing, that is producing the storm surges. So all of them are contributing together for the extreme sea level events in the Indian Ocean. This was a study by Budiscast. They looked at the extreme sea level along different coastlines. Our region, the data was not very data sparse because there is not much tide gauge data was considered. But with the available tide gauge data from whatever available from 1970 onwards, we also looked at how the extreme sea level events are increasing along our coastlines. What it is seen is that there is extreme sea level events are increasing in the Arabian Sea and mostly along the west coast of India than over the east coast of India. We have more tropical cyclones sitting over the east coast, but they are happening over an episodic periods. But when the intense systems are more forming and there's more sea level rise in the Arabian Sea, there is more severe, intense, extreme sea level events are increasing in the Arabian Sea as compared to the Bay of Bengal. And this is just an example of a recent cyclones, the Tote and Yas, and the sea level, extreme sea level associated with it. And down panel is the based on the tide gauge information from the Mumbai tide gauge. We have considered the tide gauge data from 1900 to 2020, and we identify each and every high water levels associated just with the storm surges. And blue shades is for the first initial 50 years, and this is for the later period. And we can see like in the recent years, the extreme high water levels are increasing along the Mumbai coast. So we need to understand like, okay, there are different regionally, there are different processes that are contributing to the sea level. There is a thermal expansion. If you see globally, the sea level rise is dominated by the mass, that is more than 45%. Thermal expansion is the second contributor. But for the Indian Ocean, it is the thermal expansion. More than 70% of the sea level rise in the Indian Ocean is contributed by the thermal expansion or thermospheric component. And this is from the IPCC report. But it's highlighted that more than the thermal expansion, the melt from the Greenland and Antarctica will contribute to the global mean sea level rise. So if we have to have an understanding on the sea level rise, we also need to include these contributions. How much will be these contributions will be contributing to the sea level rise? For that, we need to include all the processes. Land ice melt processes also in the model. So this is what we are working on right now. So this, anyway, I'm not going into the details. So right now, what our future plan for the IITM ESM development is, Dr. Krishna has already discussed this. We'll be including a new dynamical core so that we'll be able to do, like presently our CMIP 6, we did only T62 simulation because we have to do long simulations and we were getting a scalability of roughly 10 years per day. We have to do 2,000, 3,000 year simulations. So we cannot wait for such a long time for the simulations to get completed, and we have to evaluate it. We have to do other post-processing. Then we have to publish the data before the timeline. Like there is an IPCC has different timelines. Before that, this data has to be published for the assessment. So there was a time constraint for this. So we are including a new dynamical core. So it will enable us to go with a high resolution, but the scalability will be more. And we are also including the CISM, the Community Ice Sheet Model, in the IITM-ESM, so that we'll be able to understand how much is the impact of ice melt that is coming, because that is much more projected from the IPCC report. The ice melt will be dominating the global mean sea level rise. So we have to have that component in the system. So we are including the CISM, that is for the Greenland, and also for the Antarctica region for initially. Then we can also think about the Himalayan region later. So how much of these will be producing, will be rising. This is I am not going to the details. So this is the community ice sheet model, what we are using. So right now what we have done is that we have done more than 40,000 years of simulations. This is just with the standalone community ice sheet model. We have used the forcing from the IITM-ESM, and we have forced the community ice sheet model. And the model gives us the surface mass balance, that is the difference between the accumulation and the ablation. So that has to be fed into the IITM-ESM so that we can consider like how much is the meltwater is contributing to the sea level and other changes. So this is the standalone version being done at CCCR. So we have done more than 440,000 simulations. So the model is almost stable. And we also get the surface mass balance from the model. And this is just like the last 10,000 year simulation, wherein we can see like there is a perfect balance of the system. So this surface mass balance will be fed into the IITM-ESM, and this will be done in a serial mode first. Then once it is evaluated completely, then we will be putting it in the coupled, it will be totally coupled with IITM-ESM. So these are like our future plans. So we'll be including the new spectral dynamical core in the model, and we'll be going with a high resolution from T62 we have to see the feasibility, and we'll be including that. And we'll be including, there will be an interactive land ice model in the next version of IITM-ESM. And we'll be also putting our efforts to improve the mean state biases in the model. So this will be our CMIP 7 version for the next IPCC assessments. Thank you.
Thank you, Swapna. It's very interesting. I'll invite comments now from the audience. Go ahead.
Hello. Oh, so thank you, ma'am. It was a wonderful presentation. I wanted to ask you two questions actually. So in the CMIP 6 models, we get, I think, two sea level variables. One is dynamic sea level, and the other one is the global mean thermospheric sea level. So when IPCC is publishing these reports, how do they get the estimates for the mass change, the sea level rise due to the ice melt? That is my first question.
Yes.
And my second.
Shall I answer to that first?
Sure.
Yeah. So right, you are right. Like there is a dynamic sea level that is provided, and also the thermospheric sea level. Most of the CMIP 6 models does not have an interactive ice sheet. So what is being done is that these ice sheet models are done separately. They are done as a standalone models using the CMIP 6 forcings. And whatever is the melt happening from this land ice, they are added separately to the outputs of the dynamic component. And that is how the total sea level is estimated. So when you look at the IPCC mod outputs also, you can see different components. There will be a dynamic component, and there will be components from the melt coming from the Greenland separately, Antarctica separately. And so you have to consider all of these components to estimate the total sea level rise.
So if I want to estimate the total sea level, I have to calculate the sea level rise from the standalone ice outputs actually.
It is also provided, you can get it. It's also provided in the IPCC report. You can get those values.
And my other question is IITM providing the sea level variables for the CMIP 6?
Yeah, we do provide. We have provided the ZOS variable, that is the dynamic sea level, because our model was not having a land ice component. So we can only provide the ZOS, but ZOS also will help us to understand how much is the ice this coming without the ice melt component.
So it is available for pre-industrial control, historical and future projections?
Yes.
Thank you.
Go ahead.
Hello. Yeah.
Yes.
You had shown one picture about the increase in sea level in the Indian Ocean region.
Yes.
Along the Indian coast, there seem to be some places which had much lower. Is that actual observation? Was it some result from a model?
No, these are actual observations. This whatever figure I have shown is from the satellite data. So because we have to consider like the bathymetric coastal processes are different at different locations. Like those also will contribute to the changes in the sea level. There is an increase, global mean increase in the sea level, but the coastal processes also contribute. So we cannot expect like every region will have the same amount of rise. It will depend on like that. Just like I'm giving an example, Cochin, which is the southern coast, is expected to have a much higher sea level rise than even the northern stations. Then we have higher rise occurred over the Mumbai region. Similarly, for the east coast of India also, it is not spatially uniform. That varies because these coastal processes also contribute on a different scales.
Thank you.
Thank you very much for a very nice talk. I have one question about that IPCC report that projected sea level rises, the slide that you showed.
Yes.
There is some low likelihood, but chances of sea level rising by meters.
Yes.
Can you say what it is about, what is meant over there?
They are called the low likelihood but high impact events. That means that we are not expecting like such events can happen very often, but there is a possibility like they can also happen because there is for the models right now I have told like models are providing the dynamic sea level and the ice melt is coming separately from the Greenland and Antarctic ice sheet models. They are run on separately and these ice dynamics are so complicated. There are a lot of deep uncertainties arising from the ice melt components. So we need to consider all these. So if we are considering all actual ice melt are happening over the Greenland and Antarctica, and that may be the projected rise, but there is still more uncertainty. So we are giving a low likelihood. If it is happening, we can expect this much of rise in the future.
So this low likelihood are due to large-scale collapses of ice sheets.
Large-scale collapses of ice sheets and also happen like EMOC, collapse of EMOC. There are a lot of processes they are put in a low likelihood. They are not really very likely going to happen, but if it is happening, what will be its impacts?
So second question is that in this ice melt model, is carving of at the edges incorporated in any way?
I didn't get your question, please.
In this ice sheet model,
Yeah.
the carving of the ice and breaking off of the icebergs,
Yes.
that incorporated in any way?
Yeah, they are also considered because this is a model with all ice dynamics. So they are also included in the CISR. That is what we are using to understand these changes.
Okay, thank you.
We have one more question. Go ahead.
Hello. Yeah, you mentioned that because Indian Ocean doesn't have like the circulation, the AMOC doesn't come to the Indian Ocean, then the heat is not dissipated by the Indian Ocean to other oceans and it rises up compared to the other oceans. Now, like, so the next question is, will the glacier and the ice melt of Antarctica and Arctic, will that affect the sea level rise in the Indian Ocean because it seems that it is isolated from the other oceans?
Yeah, what I mean to say is that North Indian Ocean is isolated because our dynamics is like that. It is a little bit isolated, but we have the Indian Ocean through flow coming in, wherein the water from the Pacific is intruding into the Indian Ocean through the through flow. So that can have an impact. Similarly, this Antarctic ice melt, that is also can have an impact on the South Indian Ocean. We don't have a very deep overturning circulation, but Indian Ocean do have the shallow overturning circulations. There is a surface heat transport to the south And there is a downward heat transport to the north that generally upwells in the upwelling regions of Somalia and all those things. So we have an overturning circulation in the Indian Ocean. So this will have an impact on the sea level in the Indian Ocean. Yeah, but mostly it will be dominated by the thermal. That's the point.
Thank you.
Okay, let me just check if there's a question online. If there's a question online, just please go ahead and speak up. Okay, since nobody's speaking up, let me just ask you this, Swapna. Have you visited us in TIFR campus in Mumbai?
Not yet. Yeah,
Because-
not. Yeah.
It's a beautiful campus. It's on the ocean. And according to your graphs, in our 50-year plan, we don't have to worry. Is that right?
Yeah, that is what the models are projecting. Yes.
All right. I'll tell
Yeah,
her.
but you can expect extreme sea level events. They can happen whenever there is a cyclone passes, and it is even it don't have to hit Mumbai. If it is crossing near the Mumbai coastal region, so it will be more rise in the sea level. So that there will be like extreme events we can expect.
Will an extreme event blow up an apartment building or?
Because recently, what the Tote happened in 2021, the extreme sea level events was much higher over the Mumbai coast.
Okay. All right.
And it is projected to increase.
Okay. All right. Well, thank you so much for your talk. Thank you.
Thank you very much.